Welcome to this complete tutorial on IP addressing. By the end, you'll understand binary, how an IP address is built, the network and host parts, / notation, how to count hosts, the classes and why they are now history, subnetting, public versus private addresses, and even a look at IP version 6. This is the full picture, done right. Let's begin. Here's the plan. We build from binary up to a real IP address, split it into network and host, learn / notation and the host formula, study the classes and the correction that they're now obsolete, then master subnetting private addresses, and the move to IP version 6. Each part builds on the last. Everything starts with two ways of writing numbers. Humans use decimal, the high-level language. Machines use ones and zeros, the low-level language. An IP address lives in both at once. We read the decimal version, the computer stores the binary version. Get comfortable moving between them, and the rest is easy. Decimal is the system you use daily. 10 symbols, 0 through 9, so we call it base 10. When you pass 9, you don't invent a symbol, you carry into a new column. That's why 9 rolls over to 10. Binary uses only two symbols, 0 and 1, so it's base 2. A single one of these is a bit. 1 means a position is on, 0 means it's off. And a group of 8 bits has a special name in networking, an octet. Hold on to that word. To turn binary into the decimal we read, use this rule. Number each bit from the right, starting at 0. Each bit is worth its digit times 2 raised to its position. Add the results. Let's apply it. Convert 1010. Label positions from the right. The left bit is position 3 worth 8, then 4, then 2, then 1. Multiply each bit by its value and add 8 plus 0 plus 2 plus 0 equals 10. So 1010 is 10 in decimal. Because an octet is 8 bits, memorize these 8 place values left to right. 128, 64, 32, 16, 8, 4, 2, 1. With these, you can read any octet at a glance. Now a real octet. Take 1 1, followed by 6 zeros. Only the two leftmost bits are on. 128 plus 64 equals 192. That's not random. That's the first octet of 192 to 168. The addresses you see every day are just binary in disguise. And the fact that unlocks everything. If all 8 bits are on, you get 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which is 255. That's why every part of an IP address stops at 255. Now the definition. An IP version 4 address is a 32-bit number that uniquely identifies a device on a network. Those 32 bits split into 4 octets of 8 bits, written as decimals with same address, 2 faces, the decimal we see, and the binary the machine stores. 1 point beginners trip on. Each octet runs 0 to 255, that's 256 values, but counting starts at 0, so the top is 255, not 256. Once all 8 bits are 1, the octet is full. An IP address isn't one blob, it's split into 2 jobs. Part names the network, like a street, and the rest names one host, like a house number. A host is any single device, a PC, phone, or printer. What draws the line? The subnet mask, a second 32-bit number. Where the mask shows 255, those bits are network. Where it shows 0, those bits are host. For 198, 3 octets are never host. Inside a network, 2 addresses are reserved. The first host bit all 0 is the network IP, naming the network itself. The last host bits all 1 is the broadcast IP, reaching every host at once. You never assign those two. Everything in between, 1 through 254, is usable, 254 addresses. Writing the full mask gets tedious, so we use / notation, called CIDR. 192, 168, 100, 0, /24. The /24 simply counts the network bits. 3 octets of 8 is 24, so /24 and mask 255, 255, 255, 0 are identical. To count devices a network holds, use 2 to the power n minus 2, where n is the number of host bits. We subtract 2 for the network and broadcast addresses. For a /24, 8 host bits, 2 to the 8th is 256, minus 2 is 254. It matches our hand count exactly. Now, the classes. Historically, a network's class came from the first octet of the address, not from the mask. The leading bits set the range. Class A is 1 to 126, B is 128 to 191, C is 192 to 223, D is multicast, E is experimental, and 127 is reserved for loopback. The class fixed how big a network could be. Class A used 8 network bits, leaving 24 for hosts, about 16 million per block, for giants like national carriers. Class B used 16 and 16, giving 65,000. Class C used 24 network bits and just 8 for hosts, giving 254. Now the most important correction in this whole video. Classes are history. Back in 1993, the internet replaced rigid classes with classless addressing, CIDR, because classes wasted enormous numbers of addresses. Today you will not design a network by class. You use a prefix length, any prefix length, that fits exactly the size you need. Second correction. In the old video, we identified a class by counting the 255s in the mask. That mixed up two things. A class came from the address's first octet, but what actually defines a network, then and now, is the mask or the prefix. Always read the slash number. The mask is the source of truth, not the class. Classless thinking unlocks subnetting, splitting one network into several smaller ones by borrowing bits from the host part. Each bit you borrow doubles the number of subnets and halves the hosts in each. This is how real networks are carved up to match departments, sites, or VLANs. Let's do it. Take a look at the mask becomes 255, 255, 255, 192. 2 borrowed bits give 4 subnets in steps of 64, each with 2 to the 6th minus 2, that's 62 usable hosts. Here are all 4. Here's why our examples used 192 to 168 and 172 to 16. Those are private ranges defined by RFC 1918. Free to reuse inside any home or office. Public addresses are globally unique and routable on the internet. A router uses NAT to translate your many private addresses onto one public address. A few addresses are reserved for special jobs. 169.254 is the link local address a device gives itself when no DHCP answers. Recognize these and you'll never be confused by them. One last big picture truth. IP version 4 has only about 4.3 billion addresses, 2 to the 32, and the world ran out. The fix is IP version 6, a 128-bit address written in hex, with so many addresses will effectively never run out. Same core ideas, far bigger space. And the final correction. The old lab said devices on different networks simply can't communicate. That's only half true. On the same subnet, devices talk directly. On different subnets, they absolutely communicate, but through a router, the default gateway. Routing between networks is the entire reason the internet exists. When you actually assign addresses, follow these rules. Keep the network part identical on a subnet. Never reuse an address. Skip the network and broadcast addresses. Give every host the same gateway and DNS. And always match the mask to the real size you need. Let's lock it in. An IP address is 32 bits, 4 octets, 0 to 255. The mask splits network from host, and the slash counts network bits. Hosts equal 2 to the n minus 2. Classes are legacy. The modern world is classless and subnetted. Private ranges plus NAT stretch IP version 4. And IP version 6 is the future. That's the whole topic. Done right? That's IP addressing, from a single bit all the way to subnetting and IP version 6, corrected and complete. If it made things click, like the video and subscribe for more networking tutorials. Thanks for watching, and I'll see you in the next one.